Okay, we're going to talk about this concept of what they call Gibbs free energy. This is just a way of actually putting the values on different parts of the energy of a system. In other words, what kinds of things are contributing to a system's energy. Now, the system that we're talking about could be like one chemical equation, it could be one cell. It could, so the system would have to be defined. But let's just think of it as one, say, chemical equation or chemical happening within the cell. And what the Gibbs part is, so of course it was named after a guy that came up with this concept. What the Gibbs free energy is called Gibbs free energy is basically the energy that is available for another system to use. And that's going to include the total amount of energy that would be found in the molecules present, minus the amount of entropy times temperature. Now, the entropy is a value, remember, of disorder, and temperature is going to increase that disorder. So the more the temperature, the more entropy, and that's why they're kind of joined together. The less the temperature, kind of the less amount of disorder in general. So this is like the degree of disorder. But there would be a certain amount of entropy just in what the molecules present. So say, for example, we had a carbohydrate, which is, say, let's just say for argument's sake, 10 sugars long. And it was all connected and it had bonds between every sugar. So it then would have less entropy than 10 individual sugar molecules. And that is the 10 individual sugar molecules, because they're not joined, have more entropy. The more heat that you added to that, the more they'd move around and the more degree of disorder they would have. Okay? So it's kind of just a way of defining how much energy would be available to another system to use. So what they usually do, though, is they use the change in Gibbs, or the change in free energy, to kind of describe different systems. And that would be equal to the change in the total amount of energy of the system minus the state of entropy. All right. So anyway, the change. Let's say, for example, I start off with molecules that have a lot of energy, and then the system is exergonic and it is running downhill. So I'm releasing energy. So what's available at the end will be less than what it was to start with. That means I lost energy in the process, and I probably increased my entropy, which would make this number smaller, right? So if this number goes up, because this is minus that, then this number is smaller. So that's just an example of how you might use it. Now, another kind of concept here goes along with this. If I was just looking at this system here, so this is just a system where I have water, and on this side I have potential, and over here I have less potential, but as I just allow this system to flow, in other words, the water will tend to flow downhill spontaneously, and as it flows, it will eventually, in this system, reach equilibrium. And that would be, delta G would be less than 0. In other words, I'm losing energy. It's going to be negative. And then as it reaches equilibrium, it's going to be equal to 0. So this is just a way that they use delta G to kind of help understand systems, okay? Now notice that this system, as it reaches equilibrium, is dead in the water, so to speak. In other words, it is not functioning anymore. Nothing is spontaneously happening, nothing is running, nothing's going in and out, no light bulbs are turned on, okay? So this system, in essence, is dead. So if you look over here, this system is more like the drawing that I did of the cell, right? I have stuff coming in and I have stuff coming out, and always this water over here, or this side, has potential that will run in the delta G going downhill kind of scenario. This is called disequilibrium, And you notice that in order to be alive, you would have to be in a state of disequilibrium. In other words, if you want to keep that light bulb on, you have to keep a flow of materials and energy happening. And more like biological systems, of course, we have many parts of the system. In other words, in general, things are flowing downhill. Some parts of it might actually go uphill and then downhill, but mostly just in general, because of the laws of thermodynamics, you have to put energy in, and things will keep running downhill because energy dissipates, and I have to keep providing energy to keep that entropy level from going way down. All right, so that's kind of related to the Gibbs. And then the last kind of thing to look at is in this section is I can have molecules, or I can have things that have high potential and low. And another way of having potential is building up something on one side of a barrier and letting them, there's a high amount of them here, and they will tend to spread out. That's just kind of, the laws of thermodynamics, but it's also related to what we call diffusion, and we're going to talk about that in a little while. And, it's also related to chemical reactions, that they tend to go from high ordered systems or poly systems to the monomer system. Things tend to run downhill.